Artificial intelligence. Okay, so we've come across artificial intelligence possibly in terms of things that you've seen on a computer. You might think that a computer is very intelligent because it's able to do certain things and almost guess things, and it's able to simplify things and maybe do things in an advanced way. But in reality, a computer is really stupid. It only does what you tell it to do. Okay, so artificial intelligence is also something you might have come across in computers when you do computer programming. The if statement or if else statement, that is essentially artificial intelligence. If a certain condition should be true, then it will do a certain task. It's able to think for itself in terms of negotiating whether a condition is true or not, and then following through with a set of statements that follow. Okay, so in terms of this artificial intelligence that we're going to be looking at, the images and details do come from Russell S. and Norvig P. in their book of Artificial Intelligence: A Modern Approach. And so we are essentially going to be using those images to explain some of the aspects over here. Now, the things that we are going to be covering in this specific video is searching with state space diagrams. We're going to be looking at informed search algorithms and then also fuzzy logic. Now, I want to make it clear over here that again, there might be a few critics out there that would be saying, oh, this is not exactly as it works and stuff. And I do understand that. It's at the moment, I'm trying to explain it in basic terms, basic principles, in terms of what happens with artificial intelligence. And with this basis and foundation, it will allow for future research to happen, and but with the basic understanding of this. Also, I do often explain things that are maybe in a different way that would make things clear in my mind, even though it's not a direct correlation of what actually happens, but it helps me to understand things. Now, I'm always thinking if I can understand it in a specific way, it might assist you in a specific way. Okay, so solving problems by searching. Okay, and this is in terms of the state space diagrams that we're going to be looking at. So let's look at an example. Examples are always a good way to explain things. So if you look at a vacuum world, so in other words, you've got two rooms, you've got a vacuum cleaner, and you've got dirt that might be in different areas in this vacuum world, in the different rooms. So this is essentially what's known as a blind search. So let's say you start in state number 5 over there. Okay, so you could say, well, I'm going to go to the right to number 6, and then I'm going to suck. Okay, so is that a solution where if you were in any of these over here and you go to the right, then you can suck? Okay, you could also, with the sensorless system, start in any of these, say go to the right, which takes you to one of the right hand side's 2, 4, 6 and 8 states, and then you can suck. And then go back to the left, which takes you to state 1, 3, 5 and 7, and then suck again. So this would essentially be a solution to suck the dirt in both rooms. Yet sucking might dirty a clean carpet, so if you already got a clean carpet, you don't want to necessarily suck. Okay, so this needs to be sort of looked in a great detail. So essentially you need to then say, well, if we go to the right, if it's dirty, then suck. Okay, so this is what your state space graphs look like, or your state space diagrams. And essentially you've got all the different scenarios that you could have. In the case that we had our 8 states over here, we are now essentially placing it over here, and we try and sort of see, can we link up all the different states together in a specific diagram. Okay, so you could say, well, you're going to be checking if there's dirt. If it's not, then suck. And essentially where this all goes to is that you would, if you were given a specific problem, you would essentially go and place all your different states next to each other or in some form or fashion like this, and you might actually find that once you've actually done it, you might rearrange it slightly a bit to make it look more clearer and easier to follow. Okay, so let's look at the worst state that we could look at. That would be in terms of dirt in both rooms. So by the way, if you look at these states, essentially it's like a binary number. So you've got like, essentially you can start off here at the bottom and say, well, that's 0. If you look at the left hand side of the diagrams, the vacuum cleaner is always on the left hand side of in the left hand side room. So you could have a state of, in terms of dirt, would be 0, 0, 0, 1, 1, 0, and 1, 1. If you look at the right hand side, the vacuum cleaner is in all the right hand side rooms. And again, you've got a different scenarios in a binary state of 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so we're able to sort of have all the different combinations that we are looking at. Okay, so now if you look at this state diagram, we're looking at the worst case scenario. So there's dirt in both rooms. So if your robot is on the left hand side room, it will basically just loop back and stay in the left hand side room. It's not going to, there's no point of it to move across to the right hand side because there's dirt over there. Okay, if it does move to the right hand side, this is what would happen. It would move there, but the dirt would still be there. Okay, so we are going to be looking at that type of scenario. If you had a robot to say, well, move to the right, the state is going to remain exactly the same. It's still going to be in that specific configuration. And if you had to move to the left hand side, it will come back to this state. You still have dirt in both rooms. The vacuum cleaner would be in the left hand side room. And so essentially, if you had to now say, okay, that's fine, now we're going to go and suck from this specific room, that's going to leave us with a diagram as appearing over there. So there will still be dirt in the right hand side room. Vacuum cleaner will still be in the left hand side room, but there won't be any dirt. Okay, so if we had the vacuum cleaner move then towards the left, it would remain in the same state. There will still be no dirt over there. It would still be in the left hand side room, and there will still be dirt on the right hand side room. If, for example, this vacuum cleaner had to suck, then it would still be in the same condition. It would still be on the left hand side. There would still be no dirt over there. So essentially, from here we can move to the right hand side. We go to the right hand side. We've got a scenario that if you move the vacuum cleaner again to the right hand side room, it's still going to be in the same condition. Okay, there's still going to be dirt over there. And again, if we move it back to the left hand side room, it's going to be that the vacuum cleaner is going to be in the clean room, but there'll still be dirt on the right hand side. Okay, so we're looking at all the different options that's available over there. Okay, then let's just leave that over there for now. Let's come and have a look at this scenario over here where the vacuum cleaner was on the right hand side and there was dirt in both rooms. So now if it sucked, it would bring it down to this state where the vacuum cleaner would still be in the right hand side room. It would have no dirt in it, but there will still be dirt on the left hand side room. Okay, so if the vacuum cleaner should decide to move to the right hand side room, it will still remain in this state. If the vacuum cleaner should suck, it will still remain in this state. Then if the vacuum cleaner had to move to the left, it would come to this state. So now the vacuum cleaner would be in the left hand room. There'll be dirt over there. The right hand room would be clean. There won't be any dirt in the right hand room. Again, if the left hand if the vacuum had to decide to go to the left-hand room, it'll be still in the same state. So it won't be any difference. Yet, if it decides to move to the right-hand side, it will come to this state where it would come to a clean room still, but the dirt would be remaining over there. Okay, so once it's done that, then essentially you've got the option of sucking. And if the vacuum cleaner is in this state and it sucks the dirt, it will come to this state. The vacuum cleaner will be still in the left-hand side room. There will be no dirt in the room though. There will be no dirt in the right-hand side room as well. If the vacuum cleaner had to go to the left-hand side room, it will remain in this state. If the vacuum cleaner had to suck, it will still remain in this state. If the vacuum cleaner had to move to the right, it will move to the right and the room will still be clean over there. Okay. Now let's just pause that over there and just come back to this block over here. So we had in this scenario dirt that was in the right hand side room and with a vacuum cleaner in it. So let's say the action was to suck. It would bring it down to this specific space state diagram situation. Okay, so in this specific state, we've got then the vacuum cleaner in the right hand side room with no dirt over there. If the vacuum cleaner had to move to the right hand side room, it will still remain in that state. If the vacuum cleaner had to suck, it will still remain in the state. There will still be no dirt over there. If it moved across to the left hand side room, it will move across, but there'll still be no dirt over there. Okay, so by doing this, we're looking at all the different states in terms of that the rooms can be in. By doing the actions of moving to the left, to the right, or sucking, we can then look at what the effect would be. The final goal is to have no dirt in all locations. And we're going to have a path cost of 1 per action. So we want to sort of minimize that as much as possible. Okay, so what would be a typical problem that you might get to solve? Well, essentially, you would get a scenario where you're told, well, for example, in this example, we've got a vacuum cleaner and it needs to clean 2 rooms. You could have a scenario of you've got 2 kids and they need to be fed biscuits. And so every time you go into the left-hand kid, you're going to give them a biscuit. You go to the right-hand kid and you give them a biscuit. You might, there might be different scenarios, but essentially what you've got to do is if for example, with the kids with a biscuit, if they've already got a biscuit, you don't need to give them a biscuit. So again, you'll look at all the scenarios and you'll label it in a binary sort of form of state. Of let's say a kid with no biscuit, or kid 1 with no biscuit, kid 2 with no biscuit, kid 1 with no biscuit, kid 2 with a biscuit, kid 1 with 1 biscuit, kid 2 with no biscuit, and then both kids have got a biscuit. Yet you might be moving towards one kid. You as a vacuum cleaner in this illustration, you might be moving towards from one kid to another and then decide whether you should give it. So again, you will go and you will look in a binary format of like a 0, 0, 0, 1, 1, 1, 1, 0, sorry, and then 1, 1. And then it would be where you are maybe attending to this specific kid over here. And then again, the same scenario would be with you attending to the kid on the right hand side. Okay, and then essentially once you've done that, you will then generate the state space diagram. So essentially with the kids that are that you want to give each a biscuit, you would essentially just replace the S for sucking in terms of giving a biscuit. And essentially it would be this whole diagram just inverted. You would start with this type of scenario because there would be no kid with no biscuits, and eventually you'll move your way up to the middle state, which will move up to the states where both kids do have biscuits. Okay, so it would essentially just be an inverted view of this image. So again, you go and you look at what your different states are, you draw them out, and then once you've done that, you place it into this next to each other. You try and sort of keep them relatively in a similar sequence. So in this case over here, where it's 1, 1, and 1, 1. Over here you would have 0, 1, 0, 1, and 1, 0, 1, 0. And then over here 0, 0, 0, 0. So it will be easy with your arrows going between the different states. And then you'll just look at each condition, going to the left, going to the right. With the vacuum cleaner you'll be sucking, or otherwise in the scenario of giving a biscuit, you maybe have a G to say give a biscuit instead of the S. And you would sort of then be able to illustrate in that similar way. It would be a good example. Have two kids, they've got they need biscuits, and what would be the state space graph or diagram that you would generate to be able to show the actions that you would follow. Okay, now that we've looked at that, let's look at some informed search algorithms. And this is a very similar situation as to what your global positioning system or GPS might actually use. Depending on which models you might be getting, which manufacturers, they might have different models that are using for different scenarios. You might find that one model could be useful for a person that might be walking, while another model might be more useful for a person that might be driving a vehicle. Okay, so we're going to be using this diagram over here. And this is essentially a map of different towns. And essentially, the distances that you are seeing between each point over here is the actual distance of traveling. Okay, so let's have a look at an example. If you this is this list over here is a straight line distance to Bucharest. Okay, and Bucharest is located over there. If you look at, for example, trying to sort of see. Okay, if you look at Făgăraș, that's a distance of 176. That is the distance that you're going to be traveling from Făgăraș to Bucharest. Okay, the thing is though, is if you look at that, over here it's shown 211, while over here it is shown 176. Okay, so this 176 is a straight line distances. If you had to go from Făgăraș to Bucharest, there might be a windy road, you might have to go around a mountain or something, and eventually you would be traveling 211 kilometers. So the distances on this specific map is the actual distances, while the straight line distances are appearing over here in this table. Okay, so we're going to, for this scenario, we're going to be considering that we're starting off from Arad and we want to get to Bucharest. Okay, so we're going to be looking at the greedy best first search algorithms first. Okay, and this has got a function of f of n is equal to h of n, h being heuristic. Okay, so what we're going to be doing is we're going to be looking at the straight line distance from a certain point to Bucharest, and then we're going to from there we're going to be doing the greedy first best search, expanding each node as it appears and gets closer to the goal. Okay, and again it's best to do this by example. Okay, so what I've done is I've placed this map here at the bottom for us to use as a reference, so that we don't have to go between slides all the time. Okay, so we're starting off by Arad. Now if you look at this table over here, Arad is the straight line distance from Arad to Bucharest is 366 kilometers. So we place 366 below that. Okay, now we're going to look at all the different towns that are linked up with Arad. So that is Zărânt over there, which is placed over there. We've got Sibiu, which is over there, and we've got this city over here, which is Timisoara. You've got to apologize me for not pronouncing these town names correctly. Okay, and so we've listed all the different towns directly linked to Arad. Okay, now what we've done is if you look at Sibiu, and you look at its table over here, it is a distance of a sightline distance of 253 kilometers. So we place a 253 over there. If you look at this Timisoara, if you look at the sightline distance between that and Bucharest is 329. If you look at the sightline distance from Zerent to Bucharest is 374. So we write the numbers down below each town. And with this greedy search, you want to be greedy, you want to go for the shortest distance, that sightline distance that you want to take into account. So in this case, the smallest number between these three towns is Sibiu. Okay, now we look at all the different towns that are connected to Sibiu, and we include in Arad. So the first town is connected to Sibiu is Arad. The second town we're looking at is Făgăraș, which is over there. The third town is Oradea, okay, which is located over there. And then we've got another town over here, which is Râmnicu Vârșia. Okay. Essentially what we're doing now is that we're going to look again at the sightline distances of each of these different towns, and we're going to away from Bucharest, and we're going to write the numbers down below that. So we've got 193 over there, which does correlate with 193 over there. We've got Oradea, which is 380. If you look over here at Oradea, there we go, 380. Făgăraș is 176. Okay, so we've got 176 over there, and Arad is 366, which is 366 is located over there. Okay, now we do again a greedy search between these four options, and the smallest value is Făgăraș, so we're going to select that. Okay, so which towns are located now between are now connected to Făgăraș? Okay, so if we look at that, it is Sibiu and it is Bucharest. Right, so what's the sightline distances from Sibiu to Bucharest? If we look over here, it's 253. What's the sightline distance between Bucharest and Bucharest? Well, obviously that would be 0. Okay, so we write those values down below. So the shortest distance, we've now got to 0 over there. We've got to our location. So the shortest distance that we've got with the greedy search algorithm is from Arad to Sibiu to Făgăraș and into Bucharest. Now keep this in mind, this path that was selected, and we're going to now be doing a comparison with the next searching algorithm and see how it changes between this one. There's the next searching algorithm that we're going to be looking at. It's the Astar search algorithm. Okay, so the idea behind is to avoid the expanding of paths that are already expensive. The Astar algorithm is f of n is equal to g of n plus h of n. Okay, so g of n is the cost so far to reach n, h is the estimated cost from n to the goal, and f is the estimated total cost of path through n to the goal. Okay, so essentially with this specific algorithm, we're going to be looking at what distance have you traveled already, and then you're going to be looking at what sightline distance is there that you need to still travel. So where g of n is considered to be the actual distance you've traveled so far, so that would be going around the windy roads and maybe up a hill and down a hill. Well, h of n is still the straight line distance that is in the table. Okay, so let's look at an example of the Astar search algorithm. Okay, so again, we're starting off at Arad. So we located over there. What distance have we traveled so far? We haven't traveled any distance. Okay, so that is 0. So that's where the 0 comes over there. What's the straight line distance from Arad to Bucharest? Well, if you look over here, it is 366. Okay, so we add 366 to that. So that gives us a total of 366. Okay, now we look at the different the different towns that are connected to Arad. So again, we've got Sibiu, we've got Timisoara, which is over there, and we've got Zerand, which is over there. Okay, so if you look at Sibiu, what is the actual distance you've traveled already once you got to Sibiu? Well, that's 140 kilometers. So we place 140 over there. What's the straight line distance from Sibiu to Bucharest? Well, if we look over here at the table, we will see that it is 253. So we add 253 to it over there. The total of those two numbers added together is 393. Okay. Now we look at Timisoara. Okay, so Timisoara is located over there. What's the distance that we've traveled so far once we get to Timisoara? Well, that's 118 kilometers. So we add that over there. What's the straight line distance from Timisoara to Bucharest? Okay, so if you look over here on the table, you will see that it is 329. So we add 329 to it, and we get a total of 447. Okay, Zerand. Same thing. So we get to Zerand. What's the distance that we've traveled from Arad to Zerand? Well, that's 75 kilometers. So we have that over there. What's the straight line distance from Zerand to Bucharest? If you look over here, it's 374. So we add 374 and we get a total of 449. Okay, now we look at what's the smallest value between these three towns, and we see that it is 393. So Sibiu is selected. Right. So now once we've selected that, let's have a look at the different towns that's now connected to Sibiu. It's again Arad. It's going to be Făgăraș. It's going to be Oradea. And then it's going to be this Râmnicu Vlăsia. Okay. So again, we're going to be looking at it. So if we get back to Arad, okay, what's the distance that we've traveled so far? Well, it would be 140 kilometers to Sibiu and then 140 kilometers back. So that gives us 280. What's the straight line distance from Arad to Bucharest? That is 366. So we add 366 to that and we get a total of 646. Let's have a look at Făgăraș. Okay, so with Făgăraș, you're going to be going from Sibiu to Făgăraș. What's the distance have we traveled so far? Well, we've done a 140 kilometers over there, and we've done a 99 kilometers over there. So in total, that's going to be 239 kilometers we've traveled so far. So we have the 239 kilometers over there. And what's the straight line distance from Făgăraș to Bucharest? If you look over here, it's 176. So we add 176 to it, and we get a total of 415. Okay, let's have a look at Oradea. Okay, so Oradea, what's the distance we've traveled so far? Was this 140 kilometers that we've done from Arad to Sibiu to Oradea? So it's another 151 kilometers. So that gives us 291 kilometers. What's the straight line distance from Oradea to Bucharest? It is 380 kilometers. So we add 380 kilometers to that, and we get a total of 671 kilometers. Okay, now let's look at the final city that we've got over there. So it's at 140 kilometers over there, plus this 80 kilometers that we've traveled. Okay, so that's 220. What is the straight line distance from there to Bucharest? It's 193. So we add 193 to it, and then therefore we get a total of 413. Okay, if you look at all these different scenarios over here, or the different towns in terms of what the total is, then we will see that 413 is the smallest one. Okay, so we're going to expand that, but just keep in mind we've got 413 kilometers that we've taken into account over there. If you look at Făgăraș, that's 415 kilometers. That's a 2-kilometer difference. This is where it becomes now a situation we might need to also investigate Făgăraș, just in case that, because there is quite a close proximity with it. And you might have in your, when you're doing these type of things with specific projects, so you might have a specific scenario where you would say, well, if there is at least a 10-kilometer difference between two of the smallest values, you're going to be considering both of them. Okay, so let's have a look at the 213. So we expand this city, this town over here. Okay, now if you have a look at it, we've got the option of going back to Sibiu, which is over there. We've got the option of going to Craiova, okay, and we've got the option of going to Betelstein, okay, or Betelstein, right. I'm trying to pronounce the correct town names over here. Okay, so let's have a look. If we go to Craiova, okay, that's going to be the 140 kilometers plus 80 kilometers plus 146 kilometers that we would have traveled. So that gives us 366. What's the straight line distance from Craiova to Bucharest? It's 160, so we add it over there, and we get a total of 526. Okay, Pestesti. Let's have a look at that. So that is over there. So the total distance we've traveled so far is 97 kilometers plus 80 kilometers plus 140 kilometers. Okay, so that gives us the 317. What's the straight line distance to Bucharest? Well, if we look at the table over here, it is, that doesn't show you the final zero, but that's supposed to be 100 kilometers. Okay, so we place 100 kilometers over there. Add it together and we get 417. If we look at Sibiu, well, essentially we've traveled 140 kilometers over there, 80 kilometers over there, and then we've had to travel 80 kilometers back to Sibiu. So that gives us 300 over there. Plus, what's the straight line distance from Sibiu to Bucharest? If we look at the table, that's 253. Okay, so that's where we get that. To add it together, we get 553. Okay, now the smallest value over here is going to be 417. Yet, as I mentioned, Fagras is very close. And let's just have a look. If we had to go to Fagras, what would be the different towns that would be linking up to Fagras? Well, it would be Sibiu and it would be Bucharest. Okay, so if we again look at those different scenarios, if you look at Sibiu, we've traveled 140 kilometers plus 99 plus another 99, which will give you a total of 338. What's the straight line distance from Sibiu to Bucharest? Is 253. So we add that over there, and we get 591. Okay, if you're going from Fagras to Bucharest, what's the distance we've traveled over there? Will be 140 plus 99 plus 211, which is equal to 250. What's the straight line distance from Bucharest to Bucharest? Well, it would be 0. So we add 0 over there, and we get 450. Okay, now obviously once we've done this calculation, we can still see that Pestesti is still the smallest value of 417. So we can then continue expanding on Pestesti. Okay, so what is the different towns connected to Pestesti? Was Bucharest, it's it's Craiova, okay, Craiova, I'm getting it, and then it is this town over here, which is Nimsu Vosia. Okay, again, let's have a look at the distances that we've got to travel over there. Okay, so if we had to follow this path of towns and we added all the actual distance on this map together, we get 418. What's the straight line distance from Bucharest to Bucharest? It's 0. Okay, if you had to look at Craiova, okay, what's the straight line distance that you would have to travel to Craiova? Well, that would be from Arad to Sibiu down this way, which is equal to 455, and the straight line distance from Craiova to Bucharest is 160. So we add them together and we get 615. And then finally, if we had to go from from Arad to Sibiu, down to past Pătesti to Bucharest. Okay, it would be these distances that we've traveled so far, which added up together to be 418. And what's the distance, straight line distance from Bucharest to Bucharest? Well, that's 0. So we add 0 over there and we get 418. Now if we look at the smallest values over here, we get a final value of 418. Well, Bucharest of 418 to be the smallest value. If you look at this 418 compared to this 450 over here, it is much smaller as well. So therefore this is the best path we've got to take. Now compare this path that we've now looked at that you need to take, and you compare it into the part that we did for the greedy search algorithm. It is different, and it is giving you a better answer. It is a shorter distance to travel. Okay, so Astar have got the properties that it is a complete, it is a complete type of search. Obviously, unless there's infinity many nodes that you need to look at. The disadvantage is the time, because it is exponential, and it's exponential to the amount of nodes you've got to look at. So it takes up quite a lot of space in memory, because it keeps all the nodes in memory, but it is an optimal solution. Okay, so now that we've looked at all of the different searching algorithms, a typical scenario would be, an example would be that you would be maybe given some map. It could be a map that could be within a house. A robot's got to go through this house, and it will give you from different rooms the straight line distance. You'll have a straight line distance to maybe a specific room. So if you look at a typical house, probably one of the important areas that you might find a robot needs to go is to get to the charging station. Okay, and that might be in a specific room. So you would have a map that will be able to link up different rooms to each other. You might find that there's a room that's got 2 doors in it going to 2 different rooms. And so you have this whole map that will show you the actual distances to the different rooms. And then you would have a table that will indicate the distance from the charging station to each room that we've indicated over here. Okay, so you would essentially then go and you would draw out this this diagram using either your greedy search algorithm or your Astar search algorithm, depending on what you ask. And then you would add up the different values for the distances and then look for the shortest distance. Finally, you'll be able to then say, well, the shortest distance from this room to another room, and then by looking at how you expanded out these different rooms, you'll be able to then say which path the robot's got to go to get to the destination. Let's have a look at fuzzy logic. So fuzzy logic, you probably have come across Boolean logic, and that is like true or false, yes or no, 1 or 0. Okay, so fuzzy logic is a superset of the Boolean logic. Okay, so it builds on fuzzy set theory, which we would look at. It's a graded truth, so it's not like the Boolean logic that we've looked at, where it's true or false, yes or no, on or off, 1 or 0. It is a value that is expressed between 0 and 1. It looks at grades of membership, and so it looks at different classes that you might have. So, you know, it will be looking at, for example, what would be taken into account for a tall man to be part of a tall men class. What about different cities? What would be the criteria to have a town to be classified as a city? In Germany, for example, it is that if there's a cathedral, it's automatically a city. Even though there's some cities that are so small, about 1 to 2 kilometer in diameter, yet it would be considered as a city. So, you know, what would you also want to maybe take into account? It needs to be maybe that it needs to be a certain dimension or a certain number of people living over there. What is the class of expensive things? How do you classify if something is considered expensive or not? You know, you've got to take into account of saying, well, okay, yes, let's say a house is worth $1 million. might be considered as expensive. Yet at the same time, you might think, well, you know what, if I go and I pay um, for a piece of candy or a sweet, let's say $10, that will also be considered to be expensive. So it's all relative in terms of what you are buying. Okay. So the reasoning is using linguistic terms. Okay, so it's natural to express expert knowledge in terms of these terms. So, for example, you could say the weather. If the weather is cold, then wear warm clothes. So, how would you classify it to be cold? I find sometimes funny in South Africa, we might find being cold to be anything below 20 degrees Celsius. Yet, if you had to go to Germany, anything below anything below 5 degrees Celsius might be considered cold, but as soon as it becomes above 10, or maybe even 10 degrees Celsius, but as soon as the temperature becomes above 10 degrees Celsius, it's considered to be warm or hot even. So it's all relative terms that you need to take into account different scenarios. Right, so why use fuzzy logic? Okay, so let's look at some of the pros. It's conceptually easy to understand with natural mass. Okay, it's tolerant of imprecise data. It's a universal approximation. It can model arbitrary nonlinear functions. It's intuitive. It's based on linguistic terms, and it's a convenient way to express expert or common sense knowledge. The cons of fuzzy logic: it's not a cure-all. Okay, its crisp, precise models can be more efficient and even convenient. Okay, but other approaches might be formally verified to work. So there is a place for fuzzy logic, but you need to sort of look at the scenario and see maybe normal Boolean logic will be able to solve the problem. So there are pros and cons to it. Okay, so let's look at an example. Look at tipping, for example, a waiter or waitress at a specific place, and you might have some scaling system between 0 and 10 that will represent a quality of service at a restaurant and what the tip should be. Okay, so now we're going to be looking at an average tip for a meal, as in the USA would be considered to be 15% of the total amount of your meal. Okay, and this depends on the quality of the service provided. Okay, so if you're going to be looking at 15% always of the total bill, it's going to be a straight line. But what about the quality of the service? So now if you want to take into account the quality of the service, you might come up with some equation like this and say, well, it's going to be the straight line scenario that you're going to be taking into account. And depending on how good a service is from 0 to 10, you're going to then be able to tip the person accordingly. So that might give you either a minimum of about 5% up to a value of 25% of the bill amount you would then tip. So that's okay, but what about the quality of the food? Not that it's a waiter or waitress's responsibility in terms of having certain quality food, that's all done back in the kitchen, and so there's no influence. They've got no influence in terms of that. But maybe you do want to take into account the quality of the food. Okay, so now you've got to extend this tipping problem, and it's going to be a number between 0 and 10. It represents the quality of service and the quality of the food at a specific restaurant. So what would our tipping formula be? Well, you could come up with an equation such as this. Okay, and it will give us like this three-dimensional graph that will be looking at the tip on one axis, the food quality from 0 to 10 would be then on your x-axis, the y-axis would be your service, and then your tipping amount would be then essentially on the z-axis, if you look at it in that way, on a specific diagram. And depending on how you scale these two items, you'll be able to then get an indication of what the tipping value should be. Okay, but might want the service to be more important than the food quality. In other words, 80% for service and 20% for food. Like I say, the waiter or waitress has got no control in terms of the food quality, as that food is done all in the kitchen. Okay, so you might want to change your equation slightly to something like this. Come up with this graph. And yet if you look at this, it looks very similar to what we've had before. And it seems to be too linear. We want 15% tip in general, and then a deviation only for exceptional good or bad service. So this becomes now a situation of, you might have good food, you might have a good service, but you're looking at almost like a 30% tip that you're going to be giving. Okay, so there might be other criteria you need to then look at. And you could have a whole bunch of if-then statements or else-if statements as well, to be able to verify the different criteria you're going to be considering to be able to generate your non-fuzzy approach. Okay, so when you do that, you'll see that this is a typical plot that you would then get. So this gives a very nice plot in terms of it appears to be a little bit more mathematical, makes you look maybe a bit clever by producing a graph like this, but it is a complicated function. It's not easy to modify. You might find it's not intuitive. Imagine if you had to get to having to make a payment, and now you've got to try and figure out this, and you've got to do this calculation. You don't have a computer with you to be able to just enter in the values, and it does the calculation for you. There's many hard-coded parameters that's also included. And it's not very easy to understand, so it can cause a lot of problems. Okay, so if you look at the fuzzy approach of your tipping problem, we might want to express is if the service is poor, then the tip is cheap. If the service is good, then the tip is average. If the service is excellent, the tip is generous. That would make it more easily identified than having to actually have values associated to it. If the food is rancid, then the tip is cheap. If the food is delicious, the tip is generous. Or you could look at it if the service is poor and the food is rancid, then the tip is cheap. If the service is good, then the tip is average. If the service is excellent and the food is delicious, then the tip is generous. Okay, so all of these rules have to then be defined in your fuzzy logic system. Okay, so you could come up with, using those three rules, some other graph that appears like this. Again, looks even more complex, but it would probably give you a more accurate sort of approach to your solution. Okay, so we need to find out then how to define terms such as poor, delicious, cheap, generous. How to combine terms using the and, or, and other connectivities that we might have, and how to combine all the rules into one final output. Okay, so let's have a look at the fuzzy sets. And this is where these would now put into a mathematical representation that you can then start using for your problems. Okay, so X is essentially we're looking at subsets of a bigger value of X. So X would be, or lowercase x would be a subset of the uppercase X. Okay, so with Boolean algebra, we've looked at ones and zeros. If X is an element of set A, it's a 1. If X is not an element of set A, it's a 0. It's either true or it's false. A fuzzy set is essentially a value that's between 0 and 1. Okay, and so it's got this characteristic function. So 1 is full membership, 0 means no membership, and anything in between, let's say 0.3, 0.5, 0.7, is some graded membership. Let's look at an example. So we've got a fuzzy set and concepts that are commonly used in natural language. So John is tall, Dan is smart, Alex is happy, the class is hot. Okay, so what about another example? We look at the crisp set of tall. What would you consider to be tall? So if I had to go and I had to say to you, okay, if a person is 1.8 meters and above, would you consider them to be tall? And you would probably say yes, they are considered to be tall. Then I might say to you, okay, well, what about a person that is just 1 centimeter shorter? So they've got a height of 1.79 meters. Would you classify them as being small or short? And you might say, no, you know what? They could actually be classified as part of the tall category. And I'm like, okay, well, that's fine, but what about a person that's 1.79 meters? You know, would they be considered to be tall? And you'll be like, well, you know what? 1.79 meters is considered to be tall. So yes, 1.78 meters will be considered to be tall. And I'll be saying, okay, well, that's great. We've got now another person that's 1.77 meters tall. You're going to be classifying them as short. And you'll be like, oh, you know what? 1.78 meters is considered to be tall. That's just 1 centimeter shorter. So 1.77 meters would be considered to be tall then. Now I can keep on going like that and eventually get to what about a person that's 1.5 meters in length? And you'll be like probably saying, oh well, 1.53 meters was considered to be tall, so therefore 1.52 meters would be considered to be tall. Would it really be? So the thing is, where do you draw the line between tall and short? And so this is where this fuzziness becomes a problematic thing to look at. Okay, so again, if you look at in terms of a scale, you might say, well, a dwarf is anything that is, let's say, below 150 centimeters or 1.5 meters. But it would be some graded effect over there that we would have to have. A person would be considered to be small if they are between 1.4 meters and 1.8 meters. A person might be considered to be tall if they're between 1.6 meters and, let's say, 2 meters. And then anything from 1.8 meters above would be considered as a giant. So you'll see these diagonal lines are there. It's not a crisp sort of value. What happens if you're 1.7 meters tall? Or what happens if you're 1.9 meters tall? Are you classified as tall or are you classified as giant? And there might be different things you need to take into account. Okay, so George Cantor's crisp set operations are the following. So you've got a complement. So if A is shown over here, the complement of A is not A. So that would be whatever is outside of A. You've got containment. So over here, A is a containment of B. So A is within B. You've got an intersection. So this is the sections that are where both A and B are covering. So that would be that section over there. And then you've got a union. So that is basically looking at a subset of A, a subset of B, and joining them all together. Okay, so let's look in a bit of detail. So complement is shown with this expression. So it's essentially like a A naught, and it's 1 minus the value of A. Okay, so if you look at it, it does not belong to a set, a complement, and therefore, if you look at the sort of the explanation, a complement is a set of an opposite to the set. Okay, so if you've got a set of tall men, its complement would be a set of not tall men. If we remove the tall men set from the universe of discourse, we obtain the complement. So if A is a fuzzy set, its complement of not A or complement A can be found with this expression. Okay, containment. So containment is when a subset is part of a larger set. Okay, so if you look at a Chinese box, a set can contain other sets. Okay, so the smaller set is called a subset. So a set of tall men containing all tall men. Very tall men is a subset of tall men. Okay. However, tall men is a set. It's just a subset of the set of men. Okay. And then in a crisp set, all elements of the subset entirely belong to a larger set. So in fuzzy sets, however, each element can belong less to a subset than to a larger set. And so elements of the fuzzy subset have a smaller membership in it than in the larger set. So it's like the diagram. We've got A, which is a subset of B. It's a smaller set or category of that we've defined in terms of the larger set. You can consider it in terms of having different color candy, for example. And if you look at, let's say it's Skittles. So Skittles is a big set. It's a candy. But if you're looking for only the red candy in it, that would be a subset of the whole box of candy. So it's looking at a smaller category of the bigger category. So that's where the red candy would be then a subset of the box of candy. Okay, we've got intersection. So it's where the element belongs to both sets. Okay, so it's an intersection between two sets containing the elements shared by these sets. So for example, the intersection of the set of tall men and the set of fat men in an area where they overlap. So in fuzzy sets, an element may partly belong to both sets with different membership. A fuzzy intersection is a lower membership in both sets of each element. A fuzzy intersection of the two fuzzy sets A and B on universe of discourse X is explained in this. So basically, you've got the intersection of A and B is equal to the minimum value of A and B, and that's also expressed in this type of fashion. Okay, so it's like in the diagram where we saw the two circles intersecting each other. So the common section between the circle A and circle B, that's considered to be your intersection. And you've got a union. So it's which element belongs to either side. So a union of two crisp sets consists of every element that falls into either set. For example, the union of tall men and fat men contain all men who are tall or fat. So in fuzzy sets, the union is the reverse of the intersection. That is, the union is the largest membership value of the element in either set. So the fuzzy operation for forming the union of two fuzzy sets A and B on a universe X can be given in this expression. So A union B is considered to be the maximum value of A and B. Okay, it's also shown in that expression over there. So this is essentially looking at the two circles A and B that are intersecting each other, but we're taking into account both of them. And that's with this all aspect that we're looking at. So we've looked at all the fuzzy set operators. So let's just summarize it and see what it is. Well, we've got equality. If A is equal to B, it would be this type of format over here. We've got a complement, which should be A naught. So A naught is equal to 1 minus A. We've got containment. So that is where subset B is part of subset, or at least subset A is part of subset B. We've got unions. So A union B is equal to the maximum of A and B. And then we've got intersection, which is A intersection B, which is equal to the minimum of A and B. Let's look at this in terms of truth tables that you might have come across for Boolean logic. Okay, so not A is equal to A naught over there, and that's equal to 1 minus A. So if you look over here at this table, at this truth table, if A is a 0, not A would be 1. If A is a 1, then not A would be 0. A and B, so that's like A intersection B. I always sort of think of it in terms of this sign, looking almost like a uppercase A, and that indicates the AND, which indicates then, therefore, the intersection. And some minimum value that we've got over there. So again, if we look at this truth table over here, we've got A and B as the inputs. What would be the output? And again, you look at what is the minimum value of all inputs over here. So it's only when both are equal to 1, then the output is equal to 1. And you've got A or B, okay, or A union B. Again, this looks like a U for union, so that's how I remember that, that sign, and therefore that is the maximum of the two numbers. So if you look at A and B over here, or A or B, truth table, you look at the max value between them, and it will always be an output of 1 if any of these should be 1. Okay, so if you look at crisp rules, an example, if self is store and enemy is short, then attack. That might be something that you might want to take into account. It could be a game that you're playing. It could be, you know, it could be some alien type of game that you're considering and you're busy playing it. And you might think, well, you know what? If the enemy is short, you'll be able to probably win and beat that enemy. So therefore, as long as you are tall, you'll be safe. Okay, so the condition of the rule is if self is tall and enemy is short. Right. To check the condition is easy. Just check self for membership in a set tall and an enemy membership in a set short. So that's essentially what we're doing. But suppose that you are not tall, then the decision is not to attack. Now it comes to fuzzy rules. If self is tall and enemy is short, then attack. Okay, so the condition of the rule once again is if self is tall and enemy is short. So if self is part of the membership of tall and the enemy is part of the membership of short. So let's say you are 0.3 tall and the enemy is 0.6 short. Then that means that this condition is 0.3 true. Okay. So does that mean that we should attack? Okay, well, let's continue and sort of say, well, sometimes the consequences is inherently binary, to shoot or not to shoot. Okay, so we can simply decide the arbitrary cutoff value to be 0.5. If a condition is at least 0.5 true, then perform the action. So if in the preceding example, the condition is only 0.3 true, so the decision is not to shoot. Or we can make a random decision and the probability equals to the value of the condition. So if in the preceding example, attack if the probability is 0.3. So and again, these fuzzy rules are very much dependent on your project, on your application, on your program that you're writing, in terms of what that threshold value is that you're going to consider. Is it, you might have certain conditions in terms of threshold. And for example, if you look at firefighters, they might have a situation where there's a building that's burning. And they might say, well, if the building's burning, we're not going to go in. But there might be a condition, or there's a person that's inside of the building. Would they now consider to go inside the burning building and go and find the person? They probably would. But let's say that there was a big explosion, and the chance of anybody surviving that explosion is very small. So now would the firefighters decide to go into the burning building? Well, there's probably going to be some structural damage. There's probably going to be some destruction that's happened, and probably won't be safe to go in. What would be the purpose for them to go in if there's no survivors inside? So all these type of things we often negotiate in our mind using fuzzy rules, depending on whether to perform an action or not. Okay, so there are most of the time many rules. So if self is tall and enemy is short, then attack. You might say, well, if you're yourself big and the enemy is green, then attack. You might say, well, if you've got power that is greater than 10 and self-health that is greater than 5, then attack. So again, if you're looking at the gaming scenario, there might be certain criteria in terms of your amount of power that you've got, maybe the shooting power, maybe the amount of health that you've got. I mean, if you've been shot a few times already and you can hardly move, it might not be worthwhile to attack if you want to try and survive as long as possible. Okay, so in this case, there are a few options to make a decision whether to attack or not. The option 1 is take the majority decision. So if at least 2 of the above conditions are at least 0.5, then attack, otherwise don't attack. Take the average. So you could maybe say, well, if the condition 1 is 0.6, condition 2 is 0.6, and condition 3 is 0, then average is 0.4. 0.4 is less than 0.5, so the decision is not to attack. We could look at option 3, make a random decision with a probability equal to the average. Okay, so there's always these different options that you can take into account. It's not like a set rule necessarily. It all depends on your application, on your project that you might be performing. Alright, so that comes to the end of our presentation of fuzzy logic. Let's have a look at just an example of how we would perform a fuzzy logic expression using the rules we've just learned.
Let's look at this specific example. So in this example, we've got some or other area where there has been some or other gas leaks, and maybe, for example, a sensor is able to detect the concentration of different gases that are considered to be dangerous. It's chucked into this room, and it's able to wirelessly transmit the data back to you. And so for the detection of the dangerous gases, you're informed that that gas A, whatever it might be, is 0.4 dangerous, while gas B and gas C is 0.7 and 0.6 dangerous respectively. The combination of these gases result in a fuzzy logic expression to obtain a total danger of the environment, given as this. So this is expression. It could be one that you've developed yourself, that, if that was your specific project for that gas detecting system, in terms of looking at the different gases, looking at what concentration levels will be considered to be dangerous or not. Because there are some gases that you get that are able to ignite on their own if it goes above a certain concentration. So a very similar system I've actually done or developed to be able to determine how dangerous it is for a robot to go into a specific environment. So in this specific example, using fuzzy logic rules, how dangerous is the environment and should firefighters enter? Considers 50% to be the borderline condition. Okay, so 50% is our borderline condition. Keep in mind that if you were building a robot, you might increase this value to be more than 50%. You might say, well, anything at about, let's say, 75% would be considered to be dangerous and for a robot, because with robots, if a robot is able to save a life, then that's an advantage. But if a robot is not able, or if a robot should die or be destroyed in an explosion or so, at least a life can be saved maybe. So you might have different criteria for a robot. Okay, so for this is specifically for the firefighters to enter. Alright, so let's just go over a few things quickly to make sure. Remember that we've got, if we look at our fuzzy logic rules, we've got our not scenario. Okay, so that would be like A not, or you could have B not, and that is essentially equal to 1 minus A or 1 minus B. Right, we've got also our union, so A union B, as an example. Okay, and that would be equal to the maximum of A, max of A comma B. Okay, and then we've got A intersect B, which is equal to the minimum of A or B. Okay, so I'm just writing this over here so that we've got something to refer to. Okay, now that we've done that, I'm going to rewrite the equation over there. So danger is equal to A union B not, A intersect B not, union with A intersect C, union with A naught intersect B, union with C intersect B naught. Yeah, so let's put some values in here, except in where the A, B's and C's are. So that's equal to A is equal to 0.4 danger, so 0.4. We've got B naught. B is considered to be 0.7 dangerous, so we can say that is 1 minus 0.7. We've got A, which is again 0.4, and that is intersect with C, and C is 0.6. Okay, then we've got union A naught B, A naught intersect B. So A naught is, or A is 0.4, so A naught would be 1 minus 0.4. Okay, and that would be intersect with B, and B is 0.7. And then that would be, I'm just going down at the bottom over here, that would be union of C intersect B naught. So C is 0.6 intersect with B naught, and so B naught would be 1 minus, and what's B? B is equal to 0.7. Okay, so that's the values that we've placed now into this expression. So let's write it again, but we're going to just complete the calculations for the not expressions. So we've got 0.4 intersect with 0.3, union 0.4 intersect 0.6, union 0.6 intersect 0.7, union 0.6 intersect 0.3. Okay, so that simplifies things. Now remember, we always have to first do the brackets. That will make things easier, and then we expand from that. So if we look at this bracket over here, remember with the intersect, we're looking at the minimum of the two values. Okay, so the minimum of 0.4 and 0.3 is 0.3. Union. Or actually, let's write that out rather. Okay, so the min of 0.4, comma, and 0.3, union the minimum of 0.4 and 0.6, union the minimum of 0.6 and 0.7, union the minimum of 0.6 and 0.3. Okay, so that is equal to the minimum of 0.4 and 0.3 is 0.3. Union the minimum of 0.4 and 0.6 is 0.4. Union the minimum of 0.6 and 0.7 is 0.6. And that's union with the minimum of 0.6 and 0.3, which is 0.3. Okay, now that we've done that, we've got now this union operators in between. Remember, with the union operators, we're looking at the max. Okay, so that is equal to the max of 0.3, of 0.4, of 0.6, and of 0.3. And the maximum value over here is 0.3. So that's, 0.6. So that's equal to 0.6. That's our answer. So that is the same as saying it's a 60% danger. So obviously we've got our 50%, which is our borderline condition that we're going to take into account for firefighters. So therefore, now therefore there's a 60% danger over there, and because we not going to be considering anything that's above 50%. We're going to say firefighters firefighters should not enter. Okay, and that's our final answer.